whoops, hello, let me turn that way down. Alright, welcome to Pre Algebra. Let's get started. Today's lesson is on counting, so everyone get out your fingers. Okay, this is 1. This is 2. This is 3. No, this is not the lesson. Alright, I just had to make the joke because I've seen this on my lesson plans and I'm just going, great, we're in 8th grade and I'm teaching counting. No, it's a little bit more involved in that. What we're talking about is counting possibilities, counting outcomes, okay? Oh goodness, the groan. Alright, anyway, so there's several ways to count. We're going to watch a video detailing the 3 ways. We're going to explain why some of the slower ways might actually be preferred sometimes. But it all does boil down to a single formula at the end. So just pay attention, follow along. In your book, it's pages 370 and the top of page 371 is what you're going to be looking at. We will be talking about Kevin and his sandwich shop the whole time. Okay, so there we go.
Three different methods can be used to find the total number of possible outcomes of any situation. The first 2 methods identify every possible outcome, while the third method only identifies the number of possible outcomes needed. In this video, we will use the same example in the text to illustrate each counting method. Kevin's Deli allows customers to choose one item from each bread, meat, and cheese category. How many different sandwich options can Kevin's Deli produce? The first method used to answer this question is an exhaustive list. A table makes organizing and producing a list much easier. Notice that each column heading represents a different event category with the options for that category listed below. A methodical approach is needed when producing an exhaustive list. First, we will represent each choice by the first letter of the item. Since unique designations are helpful, rye will be represented by R and roast beef will be represented by B. A sandwich made with wheat bread, roast beef, and American cheese will be represented by the letters WBA. Going back to the table, we will add a wheat bread, roast beef, and provolone sandwich outcome to our list, WBP. This process will continue until all possible outcomes are listed and we can count the number of sandwich combinations. There are 18 possible sandwiches that Kevin can offer customers. The second method that can be used to find the number of possible outcomes is a tree diagram. More organized than an exhaustive list, the tree diagram uses branches to make sure every possible outcome is listed. After choosing either wheat or rye bread, the branches on the diagram lead to another decision point. The customer must choose a meat, roast beef, turkey, or ham. After choosing a bread and a meat item, branches are again used to indicate a decision point. Now the customer must choose between 3 cheese options, American, provolone, or Munster. Notice that it doesn't matter which meat choice is made by the customer, he still has 3 cheese options for each meat. The third and fastest way to find the total number of possibilities is to use the fundamental counting principle. The total number of outcomes can be found by multiplying the number of outcomes for each event together. In the deli example, there are 3 events: choosing a bread, choosing a meat, and choosing a cheese. Since there are 2 bread types, 3 meat types, and 3 cheese types, we can multiply 2 times 3 times 3 to find the total number of outcomes. The result is 18 possible outcomes, or in this example, 18 different sandwiches. We could add a 4th event by giving customers a topping choice: lettuce, tomato, or pickles. If we used an exhaustive list or tree diagram, this additional choice would require a bit of work to find a revised number of possible outcomes. However, using the counting principle allows us to multiply the previous possible outcomes, 18 by 3, resulting in a total number of 54 different sandwiches.
Alright, so hopefully that was clear. We're going to go right into example A. Actually, no, a couple other things. Helps if I'm on the right program. Okay.
3 different methods.
No, be quiet. Alright. Before that, the fundamental counting principle, you basically just multiply all the outcomes from each event together. That's basically it. It's a formula that just kind of keeps going, so it's kind of hard to define, but here we go. Example 8.28, how many possible outfits, whoops, that should be plural, could Michelle make using 5 skirts, 6 blouses, and 4 pairs of shoes? This assumes that everything would coordinate and go together, okay? Good? Okay, I want to eliminate that now. All right, so there's 5 choices of skirts, there's 6 choices of blouses, and 4 choices of shoes. Okay, huh? Yeah, so there's 120 possible outfits. Okay, you just multiply. Now, the fundamental counting principle, that formula, is the fastest way to find your total number of outcomes. However, the exhaustive list and the tree diagrams are still helpful in cases where we want to find out what are the odds of these events all occurring. Does that make sense? Okay, so it allows us to make sure we get all possibilities. So there are times where they're useful, and then at that point you may as well just count because you already have the list on. All right, so let's talk about example 8.2b. In 3 flips of a fair coin, what is the probability that exactly 2 flips will land heads up? So I don't want where all 3 are heads up. I don't want where only 1 or none are heads up. I want exactly 2, okay, in 3 consecutive coin tosses. Coin tosses. I think I mixed up my consonants. Moving on. All right, so at some point, my pen will work, maybe. All right, cool. All right, so either we have heads or tails from the first coin toss. Regardless of the end of the first coin toss, we have a choice of heads or tails again. Does that make sense? And then on the third one, from each one of those, we have a heads or tails possibility. What this branching does is it allows us to be able to trace all the way across and write down our outcomes, so it's very organized. So how many of these have exactly 2 heads showing? Well, 3 cases. Does that make sense? And so this allows us to find it much easier. Yeah, it can be tedious, but it can also be done with just a little bit of scratch and some determination, okay? As far as like some scratch paper and you're good, okay? So there's 3, and then we know the total number is 8, okay? We don't have to worry about trying to figure out, we don't have to use a formula because we already have it all listed. Does that make sense? Okay, so 3/8 of a chance, or 37.5%. All right, make sense? Cool, let's do some examples because I don't like teaching just by video because otherwise why would I be here? Okay, so we're going to do some practice problems together. Number 2, okay? I'm purposely doing number 2 because we reuse it later. Okay? There are 3 marbles in a bag, 1 red, 1 green, and 1 blue. John will randomly draw a marble 3 times, replacing it each time. Now, that's very important to specify whenever you're talking about pulling something out of something, whether or not you're putting it back. Because if you're not putting it back, you're changing the total of possibilities every time you do something. Does that make sense? Okay? So we need to consider that. So we're replacing it each time, so each time he draws one, he has the same odds as the first time. Does that make sense? Okay? So we have 1 red, 1 green, and 1 blue, so let's go through and get this going here. So we're going to start out, we're told to make an exhaustive list. So we'll start out with, okay, we have red, green, and blue. So let's start out with red. Okay, and the way this goes is you pick the first choice, okay, and then you go as far, or you choose all possibilities within that choice. So let's say, what happens if I get red, red, and red? Does that make sense? Yeah, red 3 times in a row. Okay, I could get red, red, and green. I could get red, red, and blue. And then I could get red, green, and red. Red, green, and green. I could get red, green, and blue. I could get red, oh goodness, red, R. Red, blue, red. I could get red, blue, green. I could get red, blue, blue. All right, that takes care of all my reds. Let's move on to what if the first one's green? Yes. Yes, you can, but we're not asked to do that this way, and we're going to use this list later. Huh? Yeah, yeah, anyway, there's the pun in there. Huh? What? I'm just going in order. Yeah. Okay, moving on. All right, so we have then, what if the first one's green? Well, we could have green, red, and red. We could have green, red, and green. We could have green, red, and blue. We could have green, green, and red. We could have green, green, and blue. We have, nope, and green. One should be green. We have green, green, and blue. All right, and then we could do green, blue, red. We could have green, oh goodness, blue, green, whoops. We could have green, 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 right? No, green, blue, green. Green, blue, green. Oh my word. This is the problem with these, okay? This right here. Okay, so anyway. And then finally we have blue. So we could have blue, red, red. We have, sorry, we have blue, red, green. We have blue, red, blue. We have blue, green. Okay, we're going to just do blue, green all the way down, and this will make it easier. And we have R, G, B. All right, and then we're going to have blue, blue all the way down. R, G, B. All right, so we have 3, 6, 9, 12, 15, 18, 21, 24, 27. There are 27 possibilities. Huh? Only if you're told it. Okay, we were told to solve this one by a list. All right, we'll see why in a future exercise. We're going to actually reuse this list. Okay? All right, the Larson family has 3 children. This has nothing to do with the Larson family here. Don't start with me. It's in the book. All right. An infant, and kindergartner, and a teenager. That's an age range. All right. Each child is either a boy or a girl. All right. So we're just trying to figure out how many possibilities, assuming we didn't know genders of the kids. Okay. And I'm sorry, that last sentence. Who knew that last sentence would be inflammatory? All right. Anyway. So here we go. First, I wasn't listening to you. What? Okay. First kid could be boy or girl, but first kid has no determination on the gender of the second kid, right? Okay, so we could have a boy or girl again for kid 2. We'll have to write that twice. Okay, and then for the third kid, it could still be boy or girl because, again, it doesn't matter what happened before. It's the same idea. Why did I not just use B and G? All right, so we just count the end of the tree. That's all you have to do. So there's 1, 2, 3, 4, 5, 6, 7, 8 possibilities. Yeah.
If you knew their age and what grade they're in, how could you not know?
Did I say this made sense? It's a math class. You can't ask. Okay, anyway, I'm kidding. It's a math class. You don't question the word problems. All right, anyway. Why does anyone need 42 watermelons? We'll never know. Anyway, why does anyone buy 8 candy bars? And you know what I mean? Like, who buys 72 apple pies? Oh, wait, I've done that. Okay, anyway. Yeah, for Pie Day 2 years ago. Oh, I bought the little 50-cent pies. Like, I didn't buy, like, the full-size pies. I bought, like, the individually wrapped pies so it would be fast and easy to hand out in class. Because I'm smart. All right, anyway. 3 6-sided number cubes, Becca, just say dice. Okay, anyway, are rolled 1 red, 1 white, and 1 black. Okay, in other words, we can tell which dice is which. Okay, most dice in a game, if there's 2 dice, they're the same color, you can't tell unless it's Catan. So we're looking at the odds of each dice getting its possibilities. So this one we're told to solve by the fundamental counting principle. It just, that doesn't fit on the slide. So anyway, all we have to do is, how many possibilities are on the red one? Okay, how many for the white one? How many for the black one? What if I told you that this is... It's 6 times 6 times 6. It's fine. It's not 666. That's the number given in the Bible. We're good. It just happens to be 3 6s. We're good. It's fine. Then I'm not making you all get it tattooed on your forehead, so we're good. All right, 6 times 6 is... So we have 36 times 6, which is what? Who already did that math? All right, cool. 216 is correct. Good for you. All right, does that make sense? Okay, as you can tell, that's the fastest way. We just can't tell you what are the odds of getting a 4 on 2 of them or something like that. Does that make sense? All right, so solve by list. I've copied the list here. Why are they not the same length? I used a fixed width font. Why? This is going to trigger me. Hold on. Hold on. Yeah, I'm triggered. Oh, my word. Please never say that again. All right. Where is Courier New? Because when in doubt, that'll work. All right. It's ugly as all get out, but it'll work. All right. I don't like Courier. I have a thing with it. All right, moving on. It's not as bad as Comic Sans, but anyway. All right, moving on. So, problem 2, we developed this whole table. I think this one might be in a different order because I think they did red, blue, green, like psychopaths. And I just copied it out of the book. So, anyway, sorry, what was I saying? Oh, yeah, so the idea is, what is the probability that John did not draw any reds on all 3 draws? Okay, that's the question. So if we have a list like this gets real easy. We just look at our cases. Does that make sense? Okay, so obviously we can rule out the whole beginning section of reds, because, like, duh. Okay, this one all has a red in it. Everything in the top row also has reds in it, so we can get rid of that, and this section has reds in it. All right, so there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 cases out of how many? 27. So it's 8 and 27. Can that be reduced? No. So that's it. If you're not told how to list the probability, just give it as a fraction, because then you're done. Make sense? Decimal or percent. Because it's going to happen a lot. All right, moving on. Number 3 was 8. Speaking of number 3, from problem 3, off to the side, whoops, I wrote below and then I moved to the diagram. What is the probability that all 3 children, oh no, the problem is below, never mind. What is the probability that all 3 children are girls? Okay, so they have 3 children, infant, kindergartner, and a teenager. Each child is either a boy or a girl. All right, so real quick, let's rule this out. The whole top section can be ruled out because you start out with a boy. So, nope. That whole section of tree is gone. All right, here, everything after this section of tree is gone. Here, it's gone because there's a boy. There's only one case in which you get 3 girls. Does that make sense? So, it's literally a 1 in how many choices? 3, 4, 5, 6, 7, 8. It's a 1 in 8 shot that all 3 are girls. Yeah, I have no comment there. All right. A probability of having a boy at all is 50-50. Because each one is its own choice. Does that make sense? The probability of having all boys is still 1 in 8. Because there's only one case where that works. What? I'm sorry, I didn't hear you. Yeah, that assumes genetic is a pure lottery and not like it's a predisposition for anything, which is a thing. But we're assuming for this that everything is like, we're assuming perfect scenario here. Yes. Hey guys, what? Well, there are 3 decisions, so I should represent 3 levels of decision. So here is decision 1. Here is decision 2, but we duplicated it because there's 2 cases from decision 1 and they don't depend on each other. Does that make sense? And then here is decision 3 all the way down. That's how I know, because there's 3 kids. Follow me? Okay. Yes? It would just be 2 times 2 times 2. You can't solve the odds of a single event like that. That's only for the number of outcomes. Back row, let's settle down. No, I don't want to hear it. I don't care. It's not my problem. Don't make it my problem. Okay. All right. Any questions on this? Cool. Homework 8.2 all is due tomorrow. Quiz tomorrow over 8.1 and 8.2. Yeah, that's kind of how this happens. All right. Distance learners, we'll see you guys later.